So in this video, we're gonna go a little bit more in depth into centripetal acceleration, or also called radial acceleration. And the symbol we use is going to be A with a little c to indicate that's centripetal acceleration. So we've been doing this qualitatively, but now we're going to start shifting over to quantifying this and getting some equations and whatnot. We have two questions. One is, how does it depend on the velocity? So as this object is moving around, how does the acceleration depend on the velocity of the object? And then how does it depend on the radius? So if we change the radius of the circle, does that affect the acceleration? It does, and we'll just figure out the relationship between them. So we need a term here. It's called tangential velocity, and we indicate that with a v and a little t. And what that is it's just the velocity of the object on the circle. So this velocity right there, called tangential because that velocity is tangent to the circle. There's another type of velocity with circular motion that we'll talk about once we get to rotation. But for now, just tangential velocity is the speed of the object as it's moving around the circle. Okay, so then we go back and we think about linear motion. And in linear, we know that the velocity of an object is the displacement over time. Remember, that's displacement. However, that's in a line. So we need to define something else for tangential velocity. And that's this little blue arc here. So if I move from this position over to this position, then I've carved out a piece of the circle. And this is called arc length. You can see it's the arc of a circle, and it's just the length of the arc. And we typically use an S for that to indicate arc length. So we can say that the tangential velocity is going to be the arc length. This would be arc length. Arc length divided by the time. So very similar. It's just that we're talking about the arc of a circle now. And if I rearrange this, then I get the velocity, the tangential velocity times time is equal to the arc length. And I'm just going to put S. So the arc length, I'll leave it, delta S. There you go, arc length. And so what we want to see is, how does the velocity, how is that going to change the acceleration? So let's think about what happens if I start increasing the velocity. So if I were to say double, we want to keep the arc length the same. Let me clarify that. So we're going to go from here to over here. So it's nice and even. So this same arc length, if I double the velocity, but I want the same arc length. So if I have twice the velocity, but I want to have the same arc length, then I got to do it in 1/2 the time. That way it cancels out. So if I go twice as fast, it's going to take me half the time to cover the same distance. And that makes sense. The faster I go, the less time it takes. Conversely, if I go slower, it's going to take me longer to do the same arc length. And this is how we're going to analyze what happens with the acceleration. So let me scroll down just a little bit, and we'll talk about changing these quantities. Go back to green. Okay, so suppose that we'll just take a case here. So I have some, let me draw a circle. Okay, so I go from some velocity here and then to over here. So that would be my initial and my final. Now if I figure out the acceleration, it would be from here to here. And so my acceleration would be that difference right here. So that would be my acceleration. And let's call this acceleration 1. So this would be v1 naught, v2 naught. And the acceleration in this case, the centripetal acceleration, would be the change in velocity. So v1, or let's just do change in velocity over the change in time. And that would be the change in velocity 1. And the change in velocity, the change in time 1. And so that's the first centripetal acceleration. Okay, so what happens if I double this thing? So what happens if instead I'm going to do double the velocity? So we're going to increase that by, we're going to double it. So we can see that the acceleration clearly is going to be much bigger. But I want to analyze over the same arc length. That's the key. So since I'm going twice as fast, it's going to take me half the time. And so I end up with a new, this was for 1. Let's do 2. So for 2, my acceleration, my new acceleration is going to be twice velocity 1 divided by the time. So again, I went twice as fast, so it takes me half the time. 1/2 of the time. I'm just going to put t1. And so this is acceleration 2. So the second centripetal acceleration, if 2 divided by 1/2 is actually 4 times v1 over t1. So the second centripetal acceleration would be 4 times, that right there is the first centripetal acceleration, a1c. So by doubling the velocity, I got 4 times the acceleration. 4 times the acceleration. So if we did it again, so if I tripled it, again, we go much longer. So now I've tripled the velocity. And I end up with much greater acceleration over here. I hope this picture is making sense. It's going to get messy. So this is acceleration 3. Well then for 3, the acceleration, the centripetal acceleration of 3 is going to be 3 times the velocity 1. And if I go 3 times as fast, it's going to take me 1/3 of the time to cover that distance of t1. And I can see when 3 divided by 1/3 is 9 times v1 over t1, which is 9 times the original centripetal acceleration. Okay, so to summarize, if we double the velocity, we get 4 times the acceleration. If we triple the velocity, we get 9 times the acceleration. So what would happen if I did 4 times the velocity? Well, you get 16 times the acceleration. So in general, we get this relationship. Acceleration, the centripetal acceleration, seems to be proportional to the velocity squared. And this is, in fact, the case. This is true. The centripetal acceleration will be proportional to the square of the velocity, the square. So 4 squared, 3 squared, 2 squared, and so on. Okay, so that's how it's related to the velocity. Well, now we're going to look at radius. Put a little bracket around this, because then we'll put them together. So how about radius? How does changing the radius change the acceleration? So now we're going to hold the velocity the same, and we want to see what happens with the acceleration. So let me get some other stuff up on here. All right. So what we're looking at is if I go half the distance. So we're looking at these two things here. Let me show you. So if I move this, you see how this other one moves along with it? And so what you should notice is, so if I have the same speed at a shorter radius, well, what you can see, or what you should see, is that the arc length is less. So we get less distance with the same speed. So let's go back to that. So velocity is going to be the arc length divided by the time. So the velocity times time is the arc length. That's tangential velocity. Now in this case, I get less arc length with less radius. And so I have greater velocity. I have less of this, so I'm going to have less of this or more of this. Wait, hold on. Okay, I was just trying to figure out how to say this without causing confusion. So these are going to move at the same velocity. However, we have less arc length. So say I have one half of the arc length. Then my velocity, and then I'm just going to put 1/2 of the arc length. So to get 1/2 of the arc length, I got to have 1/2 of the time to have the same velocity. That way the halves cancel and I get back to this. The idea is we're keeping the velocity the same. So when I take half the arc length, that means that the radius goes down, then the time also goes down. And when I increase the radius, it's going to have more arc length for the same velocity. So I'll end up with more time. And so we could do the same analysis, but what we'll see is that the acceleration is inversely proportional to the radius. And that's because of the time. If we say, okay, the acceleration is going to be the change in velocity over time. So now we increase the radius. So we go to twice the radius. Twice the radius would be twice the time. So I get delta V over 2t, which is 1/2 of V over t, which is our original acceleration. That would be like our new one. If I go to 1/2 r, then my new acceleration would be the same change in velocity, because we're keeping the velocity the same, but 1/2 of the time, which would be twice the centripetal acceleration. So as the radius goes down, the acceleration goes up, and vice versa. So we end up with this. Acceleration is proportional to the inverse of the radius. All right, let's put these two things together. So if I slide those together, what I end up with is the acceleration, the centripetal acceleration, is proportional to v squared over r, the velocity squared, and that's tangential velocity squared divided by r. And remember that to go from a proportion into an equation, this would be equals k, some proportionality constant, times v squared over r. And if we did this and plotted it, we would find that k value is 1. So we end up with our centripetal acceleration equation, v squared over r. That's your centripetal acceleration for uniform circular motion.